Right. So this is what the things that we did yesterday. Here we are using a polling method. Polling means the continuous monitoring of certain bits. Here we use an infinite loop, right now. So this won't be perfect in many cases. We need to come up with, usually in computer programming, polling will be used very rarely. We have something called interrupts. I believe we had seen about interrupts before.
Yes, sir.
When the interrupt is enabled and when that particular event happened, the program counter will be loaded with a program memory address that should be that is linked with that event, right? As far as this microcontroller is concerned, in which we are working, that will redirect the program counter value to 4, program memory address 4. In program memory address 4, we should have a branching statement or a branching statement to the address where we have a interrupt service routine. That means when that interrupt happens, what should be done? We should have a code there. If it is not there, computer doesn't know or microcontroller doesn't know what to do, it will start executing the next statements. This is how the interrupt works. Now, how to implement these interrupts in programming? We are going to see that now. For that, what I am going to do is I am going to make a copy of this one. This is a polling method. TXRX yesterday we learned both how to transmit as well as reception, right? Now today we are going to do something which is same what we did before, but we are going to use interrupts instead of polling method. We are polling, right? We are simply monitor this particular bit. If that bit is 0, we are waiting. If it is 1, then we come and then we read the register. Right now, that is how we are doing it. So these two infinite wait and which represent a polling methods will consume many machine cycles. We are going to avoid that using a concept called interrupts. Okay, now. So for that, let me make copy of this first. Right, I rename it as SCI Interrupts. Right. So after that, I remove this file from here. I add interrupts programming here. Okay, that's all. Now, many things are same. We are not going to modify those, right? We used to, as we add init serial port, we are going to have the same. There is no difference in that. This init serial port will be same, right? Okay, now after that, we are initializing 65 to TX register, and then we enable transmission. We also enable reception. We are doing those things here. Even these steps are same. After that, we have to wait infinitely. We are doing a polling here, no? We won't do that, right? But we have to enable something called because we are going to work with interrupt now. So we have to enable two things. One is global interrupts and then peripheral interrupts. These two things should be enabled. And transmit interrupts or receive interrupts. Whichever is required, we have to enable them too. So first thing is in init serial port, we are not going to touch here anything. So what we are going to do is we will do that in the main function itself. We are going to disable global interrupts. Int com. So that is what told in the requirement. Let me open the requirement now. Sorry, not requirement, data sheet. Let me open the data sheet now. So training and then embedded C for automotive. Inside we have a data sheet. Right here, we are going to explore this part. Right? We have the procedure right now. When we want to use interrupts, there is a procedure to be followed that is detailed here. The actual occur. See, they used to tell steps. I think it is here. Yeah. So using interrupt, if you are going to use interrupt, ensure that GIE and PEIE bit 7 and 6 of the INCON registers are set. If they are not set, interrupt will not happen. In the previous case, in polling method, we didn't enable them. We didn't we didn't show any focus on them. But when we are going to use interrupts, we have to do. What is the difference between the global interrupt enable and peripheral interrupt enable? Any idea that you have in your mind?
Global and peripherals.
Yeah.
Peripheral means if uh, for using this serial ports and all. If there is, I think it's rare if there is any interrupt.
Okay. What about global?
Global, I'm not sure.
It's very simple. Let us take an engineering college. There will be a dean for the college. There will be a head for the department. Yes or no?
Yes, sir.
See, when dean commands something, it is applicable to all departments in that engineering college. ECE, E&I, Triple E, whoever it is, automotive, electronics. For AI, for every department, it is applicable. Let's say when the head of ECE department want to communicate something, that is only applicable to that department. It is not applicable to other departments. Yes, no? Yes or no? In similar way, the global interrupt enable is a control for all interrupts that we have in the microcontroller. When you disable that, even if you have peripheral interrupt enable, that doesn't have any value. The peripheral interrupts are the interrupts created by the circuitry. There are different circuitries used to be there, like timer circuitry, serial port circuitry, ADC circuitry. These are different peripherals. Every one of these circuitry can produce interrupts. To enable and disable them, there are flags or control bits to enable those interrupts or disable those interrupts. Those are part of peripheral interrupt enable. Understood? If the peripheral interrupts is not enabled, though you have enabled ADC interrupts or a timer interrupts or so on so interrupts, it won't work. For all peripherals in the microcontroller have a head. That head is called as peripheral interrupt enable. Once he is enabled, only then we can enable the individual peripheral interrupts like timer interrupts, ADC interrupts like that, serial port interrupts like that. So they have the total control under the PIE, and the PIE has a master global interrupt enable. If you disable global interrupt enable, though you enable PIE, mean the peripheral interrupts or a particular peripherals interrupt like a timer interrupts or ADC interrupts, whatever it is, they will not work. It is a global masking, global disable, global command. That's why they call that as global interrupt enable. PIE means only it is applicable to peripherals. Understood? Right. So we have to enable that in a register called intcon register. So after you set these things, I believe before we do that, we have to, but while we initializing the port, we didn't disable the interrupts, I believe. Disabled. G is also not disabled right now.
Sir, while referring in the data sheet,
It's
these
on.
we are searching in this you currently USART, right? So asynchronous.
Yeah.
So is there separate, like separately for interrupt? We don't have any like chapter.
Okay. I think the interrupts will appear in every section. That's we had a different we had a lecture while we are studying about embedded system basic. I have explained you what is interrupts with some diagrams, and that is the lecture for interrupts. Once we have done that lecture, we are studying that to every peripherals will have a interrupts. Every peripherals, there are many interrupts are there. So actually, I didn't get your question exactly. If your question is like, is it the interrupt is a separate peripheral or separate module or separate thing? It is not. It is linked with every peripherals that we have in a microcontroller, right? So we have to study that along with that. No, I didn't understand your question exactly.
Yes, sir. My question is same. Like so currently we are doing a serial port, serial port.
Yeah, serial port this. Why you are
SCI.
bringing the interrupts here? That is your question, right now.
Yes, sir. Means we separate like not like that, sir. Like
Why
uh,
we are okay?
for studying the interrupts, is there any separate module so that in
The interrupts,
structured
you
way?
cannot study interrupt as a separate module because it is linked with every peripheral. Tomorrow, when I explain timer, there will be interrupts. Day after tomorrow, when I explain analog to digital converter, there is interrupts. Today, I am explaining serial port, there will be interrupts. Tomorrow, day after, there is next week, if I explain SPI, there is interrupts. The interrupts is linked with every peripheral. You have to study it along with that. You have to study that along with every peripheral. because only then you will know how to use a peripheral with interrupts and without interrupts. It's not big rocket science again. You no need to think that as a very big stuff.
Yes, sir.
It's a simple mechanism which saves many machine cycles, and that happens in every day-to-day programming, day-to-day life of a embedded system engineer or a computer programmer. Without interrupts, nothing will work in this world, meaning in the software world. So every day we use lot of interrupts. In every programming language, it is there. Every programming or every application we have interrupts. Understood? So if you try to write something without interrupts, you have to consume a lot of time. Sometimes your application will hang because you are continuously polling. When it enter into the deadlock, that's all gone. So to avoid those deadlock conditions and a continuous hanging of a module or a system, they use interrupts. So we should know how to use that with every peripheral. That's why we go for that.
Yes, sir.
Understood?
Yes, sir.
So now if using interrupts, ensure GIE and PIE of intcon register right now. So intcon bits dot here, see here, lot of interrupts we have. GIE is top one, global interrupt enable, and then intcon. Interesting. What happened to it? Peripheral PIE. Initially, when we initialize the serial port, we disable these interrupts because we don't want them to create any problem to us. That's why we disable them. When the time comes, when we enable them, after we enable our transmission controls, continuous receive, all those things, we can enable them to 1. Once you enable them, you will wait in an infinite loop. After doing the initialization, you will wait in the infinite loop. What you have done here, you have put 65 to TX register right now. So that will transfer the content 65 to TSR, transmit shift register. Once something shifted to transmit register, what it will do, it will try to shift them. How long? Till all the bits are moved out. When all bits are moved out, there is a bit called TMRT. This bit right now. Whether the TSR register is empty. TXA database TRMT. If this bit will be set to 1. If entire bits are shifted from TSR, we will get this bit 1. If that bit is set to 1, that's all. What we have to do now? Then after that, we have to push the next word to the TX register. This is what should happen right now. Yes or no? So what we are going to do now, when there is a moment in the TRMT moment, the data is transferred from TX registers to TSR. There will be a interrupt generator, TXIF, transmit interrupt flag. This flag will be set to 1 whether you enable the global interrupt and peripheral interrupts or you don't enable them. Whatever may be the case, this bit will be set to 1. Along with that, if you enable, when the interrupt is enabled, they will load program counter with the address 4. Now, where to write? I have to write a program for program to when interrupt happen, it will come to memory address 4. Yes or no? So for that, I have to write a routine. interrupt service routine, right? In the address 04, right? How to write that in embedded C, or how to write that in MPLAB IDE. For that, they have given us a sample guideline. We can use that guideline to write the interrupt service routine. Right. Let me bring that program. I think it is having some sample code for us. So it is part of, give me a sec. Let me bring it. It is C colon user, no, D colon, yeah, this is software. Projects. Here we have CAN projects. Inside that we have this one. This is the code that we wrote and experimented after going through microchip documentation. When you want to write an interrupt service routine, you have to use this keyword __ interrupts off, and then name of your interrupt service routine. It can be anything. You can have any name there. To make it meaningful, we are giving ISR. Right? After that, within that, you can open a brace and end the brace. Within that brace, you can write the program that you want to run when that particular interrupt happen. Understood? So let me copy this line and bring it to our code. This should be outside main. It is not within main. Put that outside main. So what will happen now whenever TXIF flag is set? When the TXIF flag will be set? When data from transmit register, TX register is transferred to TSR. If that happen completely, TXIF will be set. Yes or no? Come on. Vikas.
Yes, sir.
When the content of TX register is transferred to TSR, the TX register is empty. If it is empty, meaning that we can load another word to be transmitted. At that moment, they will set this bit TXIF. Moment they set the bit TXIF, as the interrupts are enabled, the program counter will be loaded with 4. When we compile and build this program, they will write a branch statement. Maybe this function will be stored somewhere. Let's say it is stored at the address some 2500 right now. As I use the keyword interrupt off, what will happen? Whenever that interrupt happen, the program counter will be loaded with the address 2500. They might have done this in the program. When you compile it, it will generate a binary program, no? Zeros and ones. In that zeros and one, these things are embedded. What embedded? When the interrupt has come, they will come here. So in the address memory address program embedded 04, they will have a branch statement to 2500. So they will come here. Whenever that interrupt happen, they will come to the memory address 2500. In 2500, what we have? As of now, we have nothing. As of now, we have nothing. They will simply, if I just say return, they will simply come out. They won't do anything. But that is not our aim. What is our aim now? We want to transmit the data. So as far as the microcontroller is concerned, when we put this data to transmit TX register, automatically it will transfer to TSR. From there it will go out. Monitoring TXIF will not make any sense to us, because that is helping to know that the data has been transferred to TSR. That's all. But when something is coming from outside, when we are receiving something from outside, in that time, what will happen? When the word is properly received, they will set a bit called RCIF. Yes or no? Receive interrupt flag. Only that we need to know. If there is a receive interrupt flag is set to 1, meaning that the word is properly received, then we can put that to TX register. So whenever there is a word received from the laptop, you just transfer to TX register. When you put that to TX register, what will happen? It will be automatically transmitted. So without have need of these lines, we can simply solve the problem. Right. So what I am going to do now, I just here I will check which one I will check. I will check for this bit. If PIR 1 bits or CIF, if it is set to 1, meaning we have received complete word in RX register. Right now, we have to transfer that to what? We have to transfer that to this particular TX register right now. So for that, what I am going to do, I need to have something called as unsigned char data. I just do it, read it for 2 times, or X reg. Right now, is it correct? I believe it's not correct. RC reg data equal to CREG. Right. Then I put the data to.
And it's repeated.
Because you want awesome doubt?
No, sir, it's repeated those
These 2 lines. Because it is double buffered. We will have 2 words of the same content. So in order to make it empty, we have to read it 2 times.
Okay.
When we read from RCRAG, we have to do that for 2 times. It is not repetition, we are doing it purposefully.
Double buffer means?
Double buffer means they will have a 2 copy of the data received.
Okay.
They will maintain it. So we have to read both to make it available for next reception. Understood?
But, sir, by reading, the content will be there only.
See, when we read it, this register, because this is register in the microcontroller. When we read that first time, they won't set this flag to 0, because RCIF flag will be set to 0 after you read. That's what here it is told, no? If you look at that reception, there. Initialize appropriate baud rate. These things are known. Enable the asynchronous serial port. If interrupts are desired, then set enable bit RCIE. Enable the reception by setting CIR, and flag with RCIF will be set to 1 when the reception is complete, and an interrupt will be generated if enabled by RCIE is set. Read the RCSTA register to get the 9th bit. This is something different. This is by reading the RCR register, and then if 8-bit received data by reading the RCREG register. Right. If any error occurred, clear the errors by clearing enable bit continuous receive enable. Okay, this we have to do. If using interrupts, ensure. Okay, I think it is a double buffered that was told here in this place. That's why I am reading it for 2 times. The REC register can be read twice to
Okay.
retrieve 2 bytes in the FIFO. Understood?
Yes.
That's why we are doing it. So even to handle the error as well, we can include these steps too. We have some steps here now, which is related to error. Because errors are more common. So what I do, if RC status bits are 1, we are resetting that, and then we read this. Maybe we can put that here itself. We no need to put that there because this is error correction only, no? So what I do, I just put that here. If there is a error, it will reset. Otherwise, if there is a reception, they will come here, and then I don't think we need it here. Right, that's all. Now the program is ready. But did he enable RCIE? I don't think so. We have enabled only peripheral interrupts. I don't enable TX transmit interrupts, but I enable receive interrupts. That's all. This will do the job. So whatever that we did before, no, same output will come for these programs too. But it is doing the same in different way. Makes sense. Any doubt you have in this program?